This is about Euler's method for differential equations. This is a numerical method for approximately finding the solution for a differential equation. It's the basis of a tremendous variety of more sophisticated methods, but it's the only one that we talk about in the BC calculus curriculum. So it's specifically, the setting is specifically for a first order differential equation. You can adapt it to higher order, but we're not going to talk about that. And we've got to have it in a form where it's solved for y prime. So a very standard form. The derivative of our mystery function is some given expression in terms of that function and the independent variable x. So I'm going to look at the example of logistic equation because we're a little bit familiar with what that should look like. And that is the derivative of y is proportional to y, but it's also proportional to some constant minus y. I'm going to make that 2 minus y. And I'm going to click in and out of a computer solution of that. Here I've got that on this Bluffton University applet. It's pretty nice. Dy dx is y times 2 minus y. And I've got the slope field for that graph, which is a really good thing to think about when you're thinking about Euler's method. So what else do we need? We need an initial condition to get an actual unique solution. So in other words, we're going to make an initial value problem. So y of some particular input is some particular output. So to make it simple, we'll say, let's look for the solution that's going through 0, 1. So right through here. So what you do to start the method is you choose some step size. You would ideally want it to be small, although making it really small is going to make it slower. A good example that's moderately small, but the numbers aren't ridiculously weird, would be h equals 0.1 for us. For a computer, you're almost always going to choose a lot smaller. And the idea is simply that you're going to take one of these slope elements, and I'm going to do this by hand in a minute. You're going to take one of these slope elements at your initial point, let's say right here where the mouse is, and you're just going to follow that for 0.1 in x, or h in x, and see where that leads you, and then repeat. It's really a pretty simple thing to do, and it really is based on the fundamental idea of what derivatives tell you. They tell you about slopes, tangent lines. So let me go to the by hand picture here. Okay, so we're going to start out. I'm going to do it in general here with h's and x naughts and everything, but then we'll get really down to cases with a table of values for the particular example. So we're going to start here at x naught, y naught, and we're going to use the fact that our mystery curve, if we drew it perfectly, our mystery curve would have exactly the slope f of x naught, y naught. Whatever combination is appropriate to this equation, whatever the right-hand side is, we're going to calculate that, and that should be the slope of a mystery curve. As soon as we get away from this point, that's going to change, but we're going to pretend that it doesn't, at least until we get to x equals h. So we're going to follow this out for a while. And I'm going to exaggerate how far we go, maybe up to like here. Let me clear out all these other slope elements for a sec. They are still in the background. They can be evaluated. And let's say this is h. And so now we're at a new value of x, which is x1. The x values are very simple. They just step forward by h in this particular kind of method. Okay. But then what's the new y value going to be? Well, we know that this distance here, let's say that's delta y, over h, that's our chosen delta x, delta y. Delta y over h should be the slope, and I chose the slope to be exactly what this function gives me at x naught, y naught. So remember, the function capital F is just an abbreviation for whatever is on the right-hand side of our original differential equation. We'll see it as y minus 2y in the example in a second. So in other words, delta y is h times that. Okay, but that's the change in y. So this point should have coordinates x1, y1. We already know what x1 is, and y1 is going to be more complicated. That's whatever height you started at, plus, of course, plus the delta y, and so plus h times f of x naught, y naught. Great. Okay. And then we're going to repeat it. Let me just do one more step in general. Let me clear out a little bit of space here. I probably shouldn't put that exactly right there. I'm going to leave the key formula there. Okay, so now we're going to go one more h. There's various methods that sometimes change the step size on the fly, but we're not going to talk about that. So we're going to go one more h. Our x2 is going to be x1 plus h, or in other words, x0 plus 2h. That's pretty simple. Okay. But then, of course, we're going to have to say, now this is where I'm going to put in whatever the appropriate slope element was here. So I erased the rest of the slope field for a sec just so it wouldn't be so busy. But it's crucial that wherever you get to, you basically access that slope field, or often called a direction field, one more time. In other words, we're going to evaluate the right-hand side, f of x1, y1, okay, and we're going to take that slope out. I'm exaggerating what would happen very much in the case of the logistic equation, but it's the right idea. Then we're going to get a new delta y, but it's going to be the same exact idea. Our y2, this is now going to be x2 comma y2, and our y2 is going to be however high this was, y1, which we've already calculated and tabulated and graphed, plus same exact idea. You're going over h at slope, this new slope, f of x1, y1. And so you get exactly the same idea. New y is old y plus h times f of wherever you were just sitting. Again, new y is old y plus the step size h times f, our master slope formula, of x1, y1. That's just wherever you're sitting now, etc. So the punchline, let's see. So let's see, I have it over here in a little more pretty printing. So we follow that slope element with slope given by f of x0, y0. And so we get x1 is x0 plus h, y1 is y0 plus h times f of x0, y0. Here's what we just did, the repeat step. We're going to add another h to x. So these guys have a very simple master formula. It's just x0 plus n times h. But here, you can't just summarize this in one simple master formula and cut to the chase. You have to do it recursively. It's each time you're creating a new y out of the old y plus the step size times the appropriate slope. Okay, so let's look at our example. Okay, so, and I'll switch to the real picture here. Okay, so we would start out at 0, 1 when n equals 0. So this is x sub 0 is 0, y sub 0 is 1. We calculate this function. It's really important that these numbers over here are given by plugging in these values over here into this function, because that's what determines which differential equation we're talking about. That happens to be 1 here. The slope here happens to be 1. Very simple. And that means this, so you're taking this number 1 plus 0.1 times this guy, and that's how we get here. Okay, so that is the essential element. Let me go back one more time to the by hand picture. That here, this would be slope 1. This is 0.1. This is 0.1. This was 1, and so this height is now 1.1 of this guy. So this coordinate x1, y1 is 0.1 comma 1.1. Okay, let's go back to the pretty picture. Okay, next we are now we're going to go over to 0.2 and x. That's pretty straightforward. Okay. Oh, sorry. Here we're at 0.1. We have y is 1.1, and now this updates. This is crucial. This is going to have slope a slightly less in this case. 1.1 times 2 minus 1.1 turns out to be 0.99. And so if we follow that slope, we're going to take 1.1 plus 0.1 times 0.99 and get this guy. Let me just write that out one time. I don't want to bore you with the arithmetic, but we're going to take 1.1 plus 0.1 times 0.99. And when we calculate that, we get 1.199. So one more time with this picture. That's going to be, in this case, we're going out and we're going to end up at 0.2 for x, and it's not much less steep in this case. This was slope 1.99. This was run 0.1. So this was 0.099. Add that to the 1.1, and we're finally at y2 equals 1.199. Really close to 1.2 if you notice. For this one, it's not curving downward very quickly yet, and so it's almost as if we had just gone up 0.1 each time. It's almost as if we had followed this particular slope twice. Then what we can see, without doing the arithmetic, you can do it in detail if you want, stop. What we get is that as x increases, y increases as well, which is the crucial thing. And this combination, y times 2 minus y, goes down slowly. And so that each time we were at 1, 1.1, a little less than 1.2, a bit less than 1.3, a little bit more noticeable, but not much, noticeably less than 1.4, and that's indicating the fact that when we start out with this 0, 1 point, we're going up, but the logistic equation, this differential equation, is telling us that as we get near y equals 2, this factor starts to bite here, and the slopes get lower, and so my rate of increase is lower. So if I actually do this, I actually have this thing set up for this particular applet. You can choose whatever method. I've chosen Euler because, which is never what you would choose in real life. To get an exact answer, you'd use one of the more sophisticated methods. But I'm using Euler. I'm using 0.1. Again, you'd use something smaller with modern computers. This you can use a lot smaller, but just to get the idea. And what you can do here is you can plug in the initial condition and submit, and it will give you the graph. Now, that's actually pretty good. That's what a logistic curve is really supposed to look like. It's not particularly inaccurate, even though that step size wasn't super small. That's because this equation is relatively tame. But let me show you, just to give you an idea of what Euler's doing and also what can go wrong. What if we cranked up the step size? This is a bad idea usually. Let me go ahead and clear all curves, but then submit this one. Now you can see the clunkiness a bit more. It's starting here, it's going a whole 0.5 up to here, and then it takes, you can see a fairly noticeable break here in terms of the slope, and it's going a lower slope to here, and then a lower slope. Now, it's really still not horrible. It's not ridiculously bad. Let's take it out a little further in x, though. I think we'll see. I might need to drive the step size up a little bit more. Let me make sure. Okay. So let's go. Yeah, so let's go. Let's try the 0.5 one more time. We'll submit. Okay, qualitatively, it's still okay. It's steep and then gets less steep and approaches an equilibrium. As you go backwards, you can also go backwards with Euler. It's not particularly hard to figure that one out either. You get a pretty good result. But if I take h up to, I think 1 is probably going to work here. Oh, actually, it's pretty good though. Oh, okay, yeah, no, 1 is a little bit special. Let's even be ridiculous, 1.5. Here we go. That'll do it. Okay, this is just really not accurate. It's a ridiculously long step size, but you can definitely see what Euler's doing. It's starting here. It's following that slope as if it never changed all the way up to here, where it's drastically different, and then suddenly realizes, oh, I got to go in a different direction, like that. Let me actually extrapolate that out a bit more. Minus 10 to 10. Let me clear that curve. Oh, no. I didn't need to do that. It actually recalculated. This is crazy. This is horrible. This is nothing like what a logistic curve should look like. In fact, it's a good way to get chaotic behavior, is use a differential equation solver like Euler and use a ridiculously large step size. It's going so far in one step that it's not paying attention to the fact that as it was going, it should have been updating the slope. And then it finally updates drastically, overcorrects, gets all this craziness. But, so even though this is a really bad numerical example, it does give you the idea more closely of what Euler's actually doing and what the process is. What you'd really do realistically, you would say like 0.01, and you would get a pretty good answer. Oh, here it's not going very far, but you get a pretty good answer. And you would also use, you can look up if you want, there's various methods. The Runge-Kutta methods are usually the industry standard, which is a variant, a more sophisticated version of Euler. It's a little bit analogous to how, say, Simpson's rule is a more elaborate and accurate version of, say, a rectangle rule.